So in the previous video we have derived the Euler's equation of motion dou p by dou rho plus g dz plus v dv is equal to 0. Now we derive the Bernoulli's equation, which is another very important equation. So this Bernoulli's equation is obtained by integrating the Euler's equation of motion, which was obtained in the previous step. So integrating that, you will get integral dp by rho plus integral g dz plus integral v dv is equal to a constant. So if we are considering the flow to be incompressible, what is incompressible flow? The density will be a constant for incompressible flow. So rho will be a constant. So this equation will be, after integration, the equation becomes p by rho plus g z plus v square by 2 is equal to a constant. So by integrating the Euler's equation, we get the Bernoulli's equation. P by rho plus gz plus v square by 2 is equal to a constant. Now dividing by g, the equation takes the form P by rho g plus z plus v square by 2g is equal to a constant. Rearranging, P by rho g plus v square by 2g plus z is equal to a constant. This is a very important relation, and this relation is known as Bernoulli's equation. Here P by rho g is called pressure energy per unit weight of flow, or the pressure head. V square by 2g is the kinetic energy per unit weight, or the kinetic head, and Z is the potential energy per unit weight, or the potential head. So this is the pressure head, this is the velocity head, and this is the potential head. So P by rho g plus V square by 2g plus Z is equal to a constant. This equation is known as Bernoulli's equation. Now the assumptions made in the derivation of Bernoulli's equation. So these are the assumptions in the derivation of Bernoulli's equation: that the fluid is ideal, that is viscosity is 0, the flow is steady, the flow is steady, the flow is incompressible, and the flow is irrotation. All these properties we have already learned in the previous classes. So these are the various assumptions used in the derivation of Bernoulli's equation. So in short, Bernoulli's theorem states that in a steady ideal flow of an incompressible fluid, the total energy at any point of the fluid is a constant. So in a nutshell, we can say that what we have derived is this statement. Bernoulli's theorem states that in a steady ideal flow of an incompressible fluid, the total energy at any point of the flow is constant, and the total energy consists of pressure energy, kinetic energy, and potential energy, or datum energy. Datum energy is another name for potential energy. Now coming to the Bernoulli's equation for real fluid, what we have derived is Bernoulli's equation for ideal fluid. So Bernoulli's equation was derived on the assumption that the fluid is inviscid or non-viscous, or in other words, it is an ideal fluid, and therefore it is frictionless. But in real fluids, all fluids are having some amount of viscosity, and they offer some amount of resistance to flow. So when we derive the Bernoulli's equation, we have assumed that there is no friction or there is no viscosity for that fluid. But in real scenario, all fluids are having some amount of viscosity, and they offer resistance to flow. So in real case, some energy will be lost in overcoming friction, which is referred to as head loss. So we have derived that the sum of pressure energy plus kinetic energy plus potential energy is a constant. That was derived based on the assumption that the flow is ideal. But in real cases, in real scenario, the flow is not ideal, and it has some amount of viscosity, and it offers resistance to flow. And since there is a resistance to flow, there occurs some amount of head loss or energy loss. In the application of Bernoulli's equation, these losses have to be taken into account. So when you apply Bernoulli's equation in real fluids, we have to consider the losses also. Bernoulli's equation for real fluids between 2 points 1 and 2 is given by. So this is the equation, Bernoulli's equation for real fluid. This is actually the equation which was earlier derived. Here it is applied for two different points, point 1 and point 2. That is why we have given the suffix 1 here and suffix 2 here. So P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus the head loss. Okay, so for real fluids, when you write the Bernoulli's equation, we have to consider the loss of head also, which is occurring because of the presence of viscosity, where HL is the loss of energy between points 1 and 2. So I hope this is clear. Here Bernoulli's equation is applied to 2 points for a real fluid.